All right, recording's on.
Good. Hello, everybody. This is yet another installment of our point distributions webinar. My name is Damir Perizovic, and today I'm very happy to introduce you to Peter Grabner, my supervisor here at Graz University of Technology, and he will be speaking about Fourier eigenfunctions in modular forms. So please.
So first of all, let me thank Ryan and Damir for inviting me to give this talk and Alexandra, of course, for inviting me to give this talk in this webinar. Actually, I think in this format, this is the first talk of this type for me. So I hope I can walk you through in a reasonable way through this talk. This is about joint work with Aram Feigenbaum and Doug Hardin from Vanderbilt, and this actually started during the semester at ISERM in 2018, which somehow seems to be ages away. And we have finished this paper sometime afterwards, but the interest in the subject was developed during that semester. So what we developed there was some type of reverse engineering of Wiasowska's construction of Fourier eigenfunction that she used for the proof that the E8 lattice is the densest lattice in 8 dimensions. And what we hoped for is that we could construct such eigenfunctions for any dimension and understand their properties, and this is what the talk will be about. So eigenfunctions in Fourier transforms can be applied for linear programming, as it was done for the proof for the E8 lattice, and then in the follow-up paper of Kohn, Kumar, Radchenko, and Wiasowska for the Lich lattice. Then more or less there was a development of an uncertainty principle that I will describe a little bit later, that is more or less in parallel to the linear programming applications of such functions. And thirdly, there is a rather new, very elaborate paper of Kohn, Kumar, Miller, Radchenko, and Wiasowska, where they proved the universal optimality of E8 and the Lich lattice in 8 and 24 dimensions. And this again uses these functions for a linear programming technique. But what is especially interesting is that they use them to find a very interesting interpolation formula that allows to interpolate a function and its Fourier transform at the same time. And for developing this interpolation formula, they need such Fourier eigenfunctions in a rather general way. And this was more or less the driving idea behind this whole development. So this I already pointed out, that Marina Wiasowska used such functions to prove a linear programming bound for the densest packing in dimension 8, and because this linear programming bound agrees with the packing with the E8 packing density, this proves that the E8 density is the densest packing. So just to give you an idea how this whole idea works in general, if we have a function from Rd to R that is admissible, which just means which has a strong enough decay to allow the Poisson summation formula to also has strong enough decay, and its Fourier transform has strong enough decay to allow the Poisson summation formula to hold. And this function satisfies the following 3 conditions, namely the value of the function and the value of the Fourier transform at 0 agree and are positive. Secondly, the function f is non-positive for large enough values of for distance larger than r, and the Fourier transform is non-negative throughout, then the density of sphere packings in Rd is bounded above by this value of the radius that occurs in the definition of the function. Or and the idea behind this, as pointed out, apply the Poisson summation formula to this function and assume that the centers of the balls are located at the points of a lattice, and then you get this bound. And this is more or less a corollary of the proof. There is equality for a lattice lambda, so for the midpoints of the sphere packing located at the points of lambda, if the function f vanishes in the points of the lattice except for the origin, of course, and the Fourier transform vanishes at all points of the dual lattice, again except for the origin. And so there is some interest, if you look at this at these properties of the function, there is some interest in finding functions that have prescribed vanishing of the function and of the Fourier transform, and this is one of the cornerstones of Vyazovska's construction. So in general, it is convenient to have f as a Schwarz function, which means that the function is vanishing stronger than any reciprocal of a polynomial, is vanishing stronger than any negative power of the distance. This also applies for all derivatives of f, which is not needed in this context, but this is the definition of the Schwarz space. And similar, you get the same order of vanishing for the Fourier transform. So this means that for Schwarz functions, the Poisson summation formula holds with very good convergence order of both sums that occur in the Poisson summation formula. And there's a second thing, namely that the space of real valued Schwarz functions is a direct sum of spaces of eigenfunctions of this Fourier transform for the eigenvalues plus and minus 1. This means that every real valued Schwarz function can be written as a sum of a +1 and a -1, -1 eigenfunction of the Fourier transform. And if one has this decomposition, the Fourier transform is formed easily. So if f the sum of f plus and f minus, then the Fourier transform is just the difference of f plus and f minus. I promised to discuss a bit this uncertainty principle. So a function is called eventually non-negative if it attains only non-negative values for the distance x large enough, and there is this definition R of f. This is more or less the last sign change of f. So this is a way to think about it in a proper way. And the uncertainty principle discusses a rather specific space of function, actually two rather specific spaces of function. I only discuss one of them. So we denote this set A plus of D, the set of functions f from Rd to R, such that f and f hat are both in L1. F hat is real valued, which implies some symmetry of f. Secondly, f has to be eventually non-negative, but the value at 0. Oh wait. Ah yes, of course. Yeah. Whereas the Fourier transform at 0 is non-positive. Of course, since the value of the Fourier transform at 0 is the integral of f, this means that f actually has to have a sign change. Since it's non-negative for large enough r, it also has to attain negative values, otherwise the integral couldn't be non-positive. And the similar condition in the opposite direction, same for f hat. F hat is eventually non-negative, but f0 is non-positive. And for this space of function, the uncertainty principle was introduced by Bourgain, Clausel, and Kahan, and they showed that the infimum over the last sign, over the product of the last sign change of f and f hat is positive if taken over all functions of this space, and possibly why some argument why the product of those two. If you rescale the argument of f, you rescale the argument of f hat with the reciprocal scaling factor, and this means that the last sign change scales with the reciprocal scaling factor, and by forming the product of RF and RF hat, you more or less remove this scaling property, and taking the square root is just a type of normalization. And so this has been shown to be a positive number, and this number is actually known only for very specific dimensions. For instance, for dimension 12 and for some small dimensions d. And it seems to be rather difficult to actually compute this number. I should say that Henry Cohn has performed quite extensive numerical computations to find estimates for this infimum for different values of d. And there is now a result that relates this uncertainty principle to things that we are interested in this talk. There's a result by Gonçalves, Oliveira, Silva, and Steinerberger who proved that the infimum is attained at the radial Fourier eigenfunction. And these are exactly the functions we are discussing in this talk. So these functions we are discussing here are producing examples for good candidates for these functions. Possibly not, so whatever. So we now come to Wiasowska's construction, which, as I pointed out, is the center part of her construction that she used for the optimality of the E8 lattice packing in 8 dimensions, and which was then adapted for dimension 24 by Cohn, Kumar, Radchenko, and her to prove that the Leech lattice is the optimal packing lattice in 24 dimensions. And just to look at this formula, we write a Fourier eigenfunction. This is what we want to obtain. We write this function f as a product of a sine squared times a function psi, which is integrated against an exponential. So one could say that this function, this integral, is actually Laplace transform with a change of variables, and I actually want to see it as a Laplace transform. So the first factor says that this function has zeros whenever, no, it has double zeros whenever the sign vanishes. So whenever x squared is an even integer, and the second term possibly has poles, as Laplace transforms usually do. And see, if we want to have that this expression is valid for all x, we would like to have that the poles of the Laplace transform compensated by the zeros of the sign factor. And originally, if you look at this expression, of course, the integral is only convergent if x squared is large enough. This is just this abscissa of convergence of the Laplace transform that one usually has. And otherwise, we would need some type of analytic continuation. And of course, if we want to deal with this function, we need to have some good expression for the analytic continuation, because we want to compute the Fourier transform. And this I already said. And the existence of an analytic continuation with prescribed behavior, with prescribed poles that we can allow, depends on the asymptotic behavior of the function psi towards infinity. And I have written down what this has to look like to actually have the right pole order. So every term of this, every exponential term in this sum produces, in the first sum produces a first order pole of the Laplace transform, and the second term, every summand in the second term produces a second order pole. And since we only have double zeros of this sine squared function, we can only allow second order poles of the Laplace transform to be then compensated by the double zeros. And then there has to be a remainder, which is an exponential that decays towards infinity. So this is just encoding the properties of the function psi that ensure that the function f that the function f has an analytic continuation to all Rn. Of course, the function f is actually a function of the distance only, a radial function. And we want to have f to be a Schwarz function. And then again, if you recall the properties of the Laplace transform, the order of vanishing of the Laplace transform for the argument tending to infinity equals the vanishing order of the transformed function for the argument tending to 0. And so we need that psi has infinite order of vanishing as a function of c for c tending to 0. Or say it vanishes to arbitrary order. And we want to, these are just some requirements on the function psi, and we try to fit that in. But before, I have to recall what Wiasowska did to rewrite the analytic continuation in a way that allows for further computation. Namely, what she did was to expand the sine squared factor in exponentials and use the exponentials to and incorporate the exponentials in the Laplace transform, and then one would have three parts of the contour of integration, namely the dashed lines in the diagram that you see. So the left part would come from adding a negative exponential to the exponential in the Laplace transform. The middle line would come from the constant term that comes from squaring out the sine squared. and the right part would come from the positive exponential coming from the sine squared. And this is just a reformulation, and then the observation was that one can change the line, the contour of integration, of course, only if psi is a holomorphic function. And the change of the path of integration was to move the lines from the left and from the right towards the middle to get these full lines that we have. So we have a contour connecting -1 to I, a contour connecting 1 to I, and then a contour connecting 0 to I, and then a contour connecting I to infinity. So 4 parts of the integral. And doing this, we just obtain this this general formula. I should say that T is just adding 1. So the transformation T that occurs here and will make occurrences of several
Peter?
Okay, I'm sorry, guys. It seems like we have lost connection.
I wasn't watching his screen. Is he off screen or?
I was actually looking at it, and it seems the picture froze. So
For me, it's just black.
yeah, it seems he is logged out.
Yeah. Yeah, sorry, everybody. Please stand by. I'm sure that he's probably going to be trying to join right back in.
Meanwhile, are there any questions? Or do we have some announcements perhaps to make?
I don't. Do we?
I can't think of anything.
Yeah, I don't think that we do.
Except to mention, of course, that after the talk, we also usually have our social time. And so please stand by if you want to chat with us. I mean, you can do it right now. Yeah, unfortunately, I don't know what's happening right now because Peter Grabner is at his home office. And so I cannot really go to his office right now.
Do you have the means of contacting him and seeing if he thinks he'll be able to join back in?
I should have his phone number, but I forgot where because I have multiple phones with me. So I could just try to look through them. Excuse me.
Oh yeah, Uhura, can you do a quick check and see if he thinks he'll be able to join back in? Thank you.
Thank you, Uhura.
Again, thank you everybody for your patience with this.
We're very sorry.
There's nothing really comparable to this in terms of if we could have in-person talks, is there?
Yes, exactly. But what we could do is just to switch around those online meeting platforms, right? We could try perhaps Windows Teams, or I don't know what's out there.
Oh, okay, so who says that Peter wasn't answering his phone. All right, at this point, I'm going to just stop the recording because otherwise it's just going to be a recording.
You can pause it.
Oh,
and now the router didn't come up, so I don't know how. Okay. Anyway, so where did we? Here. So we have this, and we have the Fourier transform, which can be computed by computing the Fourier transform with respect to this exponential, which gives this formula here. And I should say that S is transforming C into -1 over C. So these are the two generators of the modular group. And this S actually comes into play by the observation that I mentioned before, that if you rescale the function, then you rescale the Fourier transform with the opposite scaling factor, with the reciprocal scaling factor. So this T and S, they come into play in a very natural way, and they make the connection to modular functions. So this is why modular functions come into play just by the requirement that we have a Fourier eigenfunction, and of course if you have a Fourier eigenfunction written in that way. Okay, so if you compare the transformed integrals, we observe that there's a second nice property of these contours of integration. Those four parts of where we integrate are permuted by the Fourier transform, and then we get, if we want to have the function f and the function f hat to be equal, then they have to agree pathwise because of holomorphy. So we get equations connecting psi at values related by T and S, and we get the set of four functional equations that have to be satisfied by the function psi, and we have to do that for both signs. So we want to have a +1 eigenfunction, a -1 eigenfunction, and these equations come out as requirements for the transformed function to be a Fourier eigenfunction for those two values of the sign. And of course, if you look at these equations closely, then you observe that 1 and 2 are equivalent because you can transform 1 into 2 by just applying S, and the same happens for the two equations 3 and 4. They are also equivalent. So it's actually only two equations that have to be satisfied. And what we did is we worked out the full understanding of the solutions of these functional equations. And I should point out that a rather similar understanding of such functional equations was developed in this paper of Kohn, Kumar, Miller, Radchenko, and Vyazovskaya about the universal optimality of the E8 and the Leech lattice in dimensions 8 and 24. And we developed the same understanding in different languages, more or less, or in different type of elaboration. And a similar understanding was also found in a paper by Rowland and Wagner, where they also tried to do a similar a similar type of understanding of these equations that occur. Yes. So we found the solution for the +1 eigenfunction, namely the only way that these function equations can be satisfied is that psi is related to a quasi-modular form, so not psi itself, but the transformed value of psi is a quasi-modular form of a given weight. The weight turns out to be actually negative, so this means that the form cannot be holomorphic, but has to have a pole at infinity, or can only be weakly holomorphic. And the fact that this is a quasi-modular form means that it can be written as a linear combination of certain forms multiplied with powers of E2. These are the Eisenstein series. So E2 is the Eisenstein series of weight 2, which is not a modular form, but has some slightly more complicated transformation behavior under the transformation S. And this is actually what is needed. So it's not disturbing that this form has a slightly more complicated transformation behavior, but this is actually something that is a requirement that we will need later. And this gives that we can write psi as a linear combination of this form. The only thing that I want to point out that you have to look at is that the first term is multiplied by c squared, the second is multiplied by c, and the last term is not multiplied by anything but a constant. So meaning multiplication of this term by c, and keeping in mind that everything that occurs in parentheses can be expanded in terms of powers of the exponential e to the 2 pi I c. If we think one step further, we want to form the Fourier, the Laplace transform of this, and we have multiplied something with c squared. C squared times an exponential gives a triple pole of the function in terms of the Laplace transform. And we only can compensate double poles. So this means that the first term, which is multiplied by c squared, has to vanish at infinity. Otherwise, we would have problems with the existence of the Laplace transform that we use to define the function f. The second term is okay because this gives a second order pole of the Laplace transform, which is compensated by the sine squared factor. And the third term only gives single poles of the Laplace transform, which is of course compensated by the sine squared factor. So summing up, we need the first term to vanish at infinity like this exponential. The second term is allowed to have a pole at infinity in terms of the exponential of some order, which is just one less than the other one, which is just encoding the fact that we want to have a sign change exactly at distance 2n. So this requirement that we had before, the sign change at distance 2n, is encoded in these last two conditions. The first condition is encoding the fact that we cannot allow any pole order higher than 2. And of course, since we want to have the last sign change as small as possible, we want to achieve this with n as small as possible. So n is still a parameter here that we want to choose as small as possible. And on the other hand, we know that we have to allow some polar order at infinity because of the negative weight that we have built in from the very beginning. So we can only achieve forms that are weakly holomorphic from this. And so what we have done is we have multiplied everything with a power of delta, the simplest cusp form. And then this gives us a holomorphic form of 12n for the weight of delta and 4 minus d over 2 for the weight of the function psi. And summing up the conditions we had before, we have n plus 2 homogeneous linear conditions that we have to satisfy from the list of equations that we had before. So if you look at this, if we multiply this by delta to the n, this just compensates the polar order in the last equation. There's one equation left from the second equation, and there are n plus 1 equations for the first equation. So this just says we have n plus 2 equations to be satisfied. And these are homogeneous linear conditions. And now we have to provide a space of functions that has large enough dimensions to actually allow a non-trivial for a non-trivial solution of these n plus 2 homogeneous linear conditions, meaning we need to have a space of dimension n plus 3 at least to find the function, find the non-trivial function f that satisfies these conditions. And we have to take this from a space of quasi-modular forms. And this space has some weight depending on n and d. And this dimension of the space is the integer part of w over 4 plus 1. And from this we can compute a bound for n, for this parameter n. And of course we want to choose n as small as possible. And choosing this value of n, which is then the smallest possible value of n, is the smallest integer larger than d plus 8 over 16. We get this value for the weight. And this value for the weight. And this then describes the correspondence of the how the dimension is transformed into the weight, and also how the dimension gives a value of n. And n, as I pointed out before, is the last sign change of the Fourier eigenfunction that we are producing. Okay, so if you look at this is d multiplied by 12 over 16, which is 3/4, minus d over 2, which says w is roughly the dimension over 4 plus something. So the correspondence between dimension and weight is roughly that the weight is growing like the dimension divided by 4. Okay, and this was actually I think the most interesting part of our paper, that we have quasi-modular forms that have prescribed vanishing orders. These homogeneous linear conditions that I was talking about are actually vanishing orders of certain sums of modular forms. And it turned out that differential equations are a very convenient method to keep track of these vanishing orders. This is something that at least we teach some of our engineers, that if you have a differential equation that you want to solve in terms of holomorphic functions, you make this ansatz as a power series, and then you try to compute coefficients by comparison of coefficients. This is actually what is behind here. There's an ansatz dating back to Frobenius, and you can actually encode these vanishing orders that we have in certain properties of the differential equation. So the differential equations that we found look like this. We have actually I didn't write it in terms of usual derivatives, but I wrote it in terms of the Serre derivative, which makes it a little bit more convenient. The Serre derivative more or less compensates the fact that the derivative of a modular form is not longer a modular form, but the Serre derivative transforms modular forms into modular forms. And if you change the parameter w a little bit, it also transforms quasi-modular forms into quasi-modular forms. So this is for this E2F term too, which does this trick. And actually D is not quite the derivative with respect to C, but we divide through by 2 pi I, because there's a 2 pi I everywhere, and otherwise those 2 pi i's would more or less mess things up. So this is just a derivative that takes into account those 2 pi i's that occur everywhere, and secondly, it makes sure that the derived functions are still in the same space. And actually, if you look at this function, if you look at this differential equation, you can easily work out that this differential equation has two properties. It is invariant under S and T. Yes, because the Serre derivative is built so that the derived functions still have still behave well under S and T. E4 and E6 are modular forms, so they behave well under S and T anyway. And secondly, the characteristic exponents in terms of this Frobenius ansatz are 0, 1, and W minus 4 over 4, which are actually the values that we prescribed before. And actually, there's a small thing that this equation, as I've written it down, only works for W divisible by 4. And there's a similar, slightly more complicated equation if W is congruent to 2 modulo 4. But I just want to give you an idea of how things work. So you see there is a rather nice looking differential equation. And this differential equation actually takes care of all the properties of the functions that we want to have at once. So if we find a solution of this, we can work out that the solution is a quasi-modular form. And secondly, these 3 conditions that we had before on the order of vanishing, I'll show you them again. These 3 conditions on the orders of vanishing, or on the polar order that we allow, are satisfied automatically. So the differential equation does the trick of just satisfying all the conditions that we had imposed before. And this is what I said. And it shows secondly that the equations that we are solving are actually independent. So at first glance, we are writing down n+2 equations for n+3 variables. And this says, okay, there is a space of dimension at least 1 for the solution. The solutions form a space of dimensions at least 1. But we cannot rule out that the space could have larger dimension, which would mean that we could still do better than we had thought. But the differential equation actually says the orders of vanishing are exactly those that we had prescribed. And this means that there is no more degrees of freedom than we had assumed. Okay, and there's a second feature that comes from a differential equation, namely the differential equation allows to write down a recurrence for the functions fw. And actually there are two recurrences. There's this one that I showed you, which involves a derivative. There is a second recurrence equation, which is a three-term recurrence, which is, say, a bit more complicated to get and also gives it, in my understanding, less insight than this equation here. Actually, I use this equation to produce f for large values of w, and this really works out very quickly because one can implement the CR derivative very, very easily. And secondly, if one has a solution for w divisible by 4, one can also produce the solution for w congruent to modulo 4 by just applying a CR derivative once. So for the case of epsilon minus 1, so for the negative eigenfunctions, we also got the full understanding of the solutions of the functional equations that I've written down before. There was a strange thing that took me quite a while to understand, namely this log lambda term. I first thought, no, this cannot happen because log lambda doesn't have anything to do, but then it really worked out that this term had to occur, and f is this is a rather strange mixture. There is f, a holomorphic modular form for the full modular group, and omega, the second term, is only modular for gamma 2 as as a congruent subgroup of the modular group. And log lambda and lambda is the modular function for gamma 2 for this group. And secondly, this function omega has to satisfy, say, a strange functional equation that also took me a while to understand properly. First, tried to get some overview of how to produce the solutions. But if one looks at it at the right way, one can see that the solution space of this equation is two-dimensional over the field generated by the modular function j. And as soon as one has this, one more or less has a full overview over the solutions. And so we produced, or we actually proceeded in a similar way as before. So we multiplied away the poles that the functions could have, and again, n should be chosen to be minimal so that all the linear conditions we have can be accommodated. And a similar development as before showed that there is a differential equation satisfied by these functions. And actually, the strange thing is that the differential equation is the same differential equation as for the other function, except that the parameter w has to be shifted by 2. Pardon me?
Sorry.
Is there any comment, question? Hello?
Maybe there's a remote chance.
Hello? Okay, so
I think someone was accidentally had unmuted themselves and then just muted themselves again.
okay. Yeah. It was not clear whether it was a comment or just some. Okay. Anyway, so the solutions come with a linear recurrence again, and by this linear recurrence, we have a full understanding of the solution space. So that's the important part. So actually, we went the other way around. We had those equations that we solved, and we tried to understand how the equations were formed and how the solution space looked like. And only in the end, we found this differential equation, which then put everything into one framework and made it much more clear what was going on. Okay, so this more or less gave an overview of the result of our reverse engineering of this approach of Wiasowska's to produce these eigenfunctions. And so we have a method now to produce radial Fourier eigenfunctions which vanish at large enough even values of the squared distance. Actually, this only works for dimension divisible by 4 because otherwise there are no, at least no classical modular forms behind. And actually, this is the second part of Wiasowska's proof. She had to prove that the Fourier eigenfunctions she produced are positive in a certain range. And to prove this, one needs some properties of the underlying modular forms or quasi-modular forms F. And of course, the forms are positive along the imaginary axis if all the Fourier coefficients of the modular form are positive. And we could actually prove this for weights up to 100, which I think is dimension up to 392 or something. So for rather large dimensions, we could prove that the Fourier coefficients are positive. And actually, in the course of doing this, we found that this is related to a conjecture of Kaneko and Koike, where they conjecture the positivity of the coefficients of certain quasi-modular forms, which are very much related to the forms we were looking at. And of course, this is not proving for all of them, but only up to some, say, reasonably large number. And we also collected a number of Fourier eigenfunctions for small dimensions. I think small means up to 48 or so. And we discussed the properties of these functions that we get. And actually, the unfortunate part of the whole story is that except for dimensions 8, 12, and 24, no functions are good enough to actually prove anything about packing or about this uncertainty principle. But still, I think the functions that are given by this procedure are of some interest of their own, and I hope that I could give you some insight into Wiasowska's approach to the E8 packing problem and also to this collection of results on modular forms. Thank you very much for your attention.
All right, thank you very much for the nice talk. So let's applaud our speaker, or just push the applause button. All right, thank you guys. So are there any questions, please?
So I have a question. So you were saying, so right here on the slide it even says, so right, so you were saying it's necessary for the dimension to be divisible by 4, otherwise classical modular forms aren't known, or you said something like that?
So the point is that then you have, so this would give even weights. If you have the dimension divisible by 4, the weight you get is even, and otherwise you would have either odd weight or weight even only half integer. And then you are in a different type of machinery.
Okay, so it could possibly, so it's maybe still possible to do. It just you'd have to change what you're doing.
Yes, So for instance, I should mention there's a paper by Radchenko and Vyazovska where they produce Fourier eigenfunctions on the real line. And what they can do, they can prescribe the value of the, wait just a moment. What they are doing is they derive an interpolation formula for Schwartz functions on the real line. And they can prescribe the function and the value of the Fourier transform of the function in certain points.
Nice.
And in order to do that, they study certain forms of weight 1/2. So actually theta functions, or something that they express in terms of theta functions. And this also works, but I'm not sure how far one can go in other dimensions. But the machinery is quite different, I think, if the dimension is not divisible by 4.
Thank you very much. Any more questions? Well, I have one basically on this last line on your slide. It says you cannot really obtain good bounds except in dimensions 8, 12, and 24. Is there something special about those dimensions, or was this just a lucky coincidence?
It's not clear from the understanding of these functions why 8 and 24 play this special role with respect to packing. You can write down the functions and then you see for these 2 dimensions they are especially good. Otherwise, there's at least I don't know about any explanation of this. But of course, the coincidence still is that before it was known that for for dimensions 8 and 24, the linear programming bounds developed by Kohn and Elkis would come very close to the actual bounds given by the existence of the E8 and the Leech lattice. And and in all other cases, the linear programming bounds and the known lattice packings had some rather large difference. And so, of course, this doesn't explain why 8 and 24 are special, but the intrinsic explanation behind is that E8 and the Leech lattice are special. And dimension 12 for the uncertainty principle is a similar thing. So just from the numerical experiments that Henry Kohn had done, one could see that for dimension 12, the zeros of the function that would achieve, at least or would numerically achieve the best possible bound for the uncertainty principle, had zeros exactly at distances squared equals to the even integers. And for all other dimensions, this is only this is only an approximation. So the zeros of the numerical best possible solution of the uncertainty principle, the zeros are close to distance squared equals 2n, but not quite. But this is no explanation. This is just that this a description of phenomena.
All right, thanks. So are there any more questions? Also, feel free to use the chat.
Since you're in Austria, would it be more appropriate instead of clapping if we were all knocking on our desks?
This is at least the academic way of clapping, but whatever you like to do is fine for me.
Okay.
All right, I guess if there are no questions for this recording part, let's stop the recording and see if there are more questions afterwards.